Hello, my name is Friederike Bruns and welcome to my presentation of our work-in-progress paper titled Modeling of Real-Time Communication for Industrial Distributed Automation Systems. Distributed automation systems are increasingly used nowadays, and each device can have an own understanding of time due to their modularity to guarantee the reliability and predictable behaviors necessary. This can be achieved by making use of new industrial technologies like time-sensitive networking and the new standard IEC 61499. TSN is Ethernet-based and has been proven to meet real-time requirements of environments like industrial automation networks. We propose a design methodology to verify real-time communication in IEC 61499 systems and prove that the time behavior of an application using non-local communication can be verified. The IEC 61499 standard provides various models for distributed industrial automation systems. In the system model, the overall system is represented as several resources that are connected over a communication network and control a common process. An application can be implemented to run on one or more resources and therefore may include non-local communication. The application can be represented as an application model which contains several function blocks. The function blocks can be mapped on the resources in the system model. For now, non-local communication is represented as a dotted line and cannot be further specified. The introduction of contracts enables the validation of real-time behavior of the application. Under a certain assumption, contracts can give a guarantee for real-time behavior of a function block or a composition of them. The proposed scheme of contracts can be integrated into existing IEC 61499 modeling and runtime environments. Therefore, each function block of the application is now equipped with a contract. For example, contract C1 guarantees a reaction within 2 milliseconds if its assumption of an entry occurring every 10 milliseconds is fulfilled. The overlaying contract C specifies assumptions and guarantees for the overall application, but also the non-local communication does take a specific amount of time, and to be able to attach a formal behavioral specification for the overall application, it is also necessary to take its timing behavior into consideration. We highlighted this part because we now need to take a deeper look into the process of non-local communication. Local communication can basically be divided into three parts: the publish block, which is used to send multicast messages to the network, the actual transmission of data, and the subscribe block, which receives such multicast messages. Both the publish and subscribe block have to be handled on a specific device and therefore can be mapped onto the resources 1 and 2 in the system model. The actual communication has to be mapped onto a specific resource in the communication network. After introducing these communication blocks, it is now possible to define contracts for each of them. For example, it is assumed that an entry occurs every 10 milliseconds with an offset that includes the time taken by previous function blocks, which guarantees that a reaction occurs within 1 millisecond. We evaluate this concept with a C++-based proof-of-concept simulation, which shows the correctness of our proposed representation of non-local communication and also makes it separately measurable. Therefore, the magnitude of the timing can be determined, and it can be computed how much time the simulation takes for specific function blocks. With this information, it is possible to add contracts and verify the correct timing behavior of the simulated system. Therefore, we implemented two devices which are connected over a communication channel. Both contain part of an application with each three function blocks mapped onto them. With this simulation, a time trace is created and can be verified against their ideal component contract structure. Thus, the first column shows the function block information, the second shows the execution time trace, the third refers to the valid time according to the time traces and corresponding contract, and the last shows the pass-fail information. After the contracts are kept for the first few function blocks, the transmission of data takes longer than guaranteed by the specified contract. This also leads to failure of further contract. To assure correct time behavior, it is possible to either adjust the contracts by using time intervals in which an entry or exit event may occur, or by adjusting the application. If the application is adjusted, the generated time traces keep the ideal component contract structure. Following our proposed design methodology to develop a simulation-based verification environment, it is possible to verify real-time communication in IEC 61499 system. With integration of non-local communication, it is possible to create a separately measurable simulation. This timing behavior of an application can be analyzed, and additionally, contracts can be used to verify a defined schedule is kept. This enables post-mortem trace-based timing verification. Our simulation does not cover any timing phenomena of real implementations of periodic systems like jitters or clock drift yet. Therefore, in future work, we will propose an extension of the system methodology where also behavior and timing specification is included. This is supposed to be a model which is executable on actual hardware.